Okay, good evening, everyone. If you don't know me, my name is Perumal Nithiyarasu. I am the Associate Dean for Research, Innovation and Impact, Science and Engineering at Swansea University. So, on behalf of University and Zienkiewicz Lecture Committee, I am delighted to welcome you all to our annual Zienkiewicz Lecture. Those who may be less familiar with Oleg Zienkiewicz, I would like to highlight his notable legacy. Oleg worked in Swansea University's Civil Engineering Department from 1961 until his passing in 2009. He is internationally recognized as one of the founding fathers of the finite element method and played a pivotal role in nurturing generations of leading researchers here in Swansea and around the world. So if you don't know what finite element is, please go to Google and you will get an AI answer. Oleg never stopped working. In fact, his 8th edition of the book, co-authored by myself and Bob Taylor from University of California, Berkeley, came out earlier this year. So even after passing, he was making us work on the book, right? Some of you may immediately recognize that, who knew Oleg in the past. The other thing I would really like to briefly highlight is the relevance of today's lecture to Swansea University. We have been developing fusion-related research for nearly 5 years now, and the area in Swansea has rapidly expanded through support from UK Atomic Energy Authority, EPSRC, recently Fusion CDT, and most recently the Foster program. Around 4 million has been secured through fellowships, studentships, and research projects. More importantly, the new Foster funding will further strengthen fusion in Swansea by creating a new MSc Fusion Engineering program, which is really good news for us. The university is also strongly committed to this field, and it is encouraging to see many of our graduates are actually taking up job in UK Atomic Energy Authority. Before I invite the Vice Chancellor to introduce our speaker properly, I would like to acknowledge some of our distinguished guests and sponsors. We are pleased to have Professor David Sweeney here, Deputy Chair of MEDER, with us this evening. We are also joined by Professor Howell Thomas, President of Learned Society of Wales, and Olivia Harrison, the Chief Executive. I am especially pleased that Krisha, Oleg's daughter, is joining us today. And also, I have met several colleagues from industry today, especially from CS Connected. Thank you for coming along. I would also like to extend my sincere thanks to our external sponsors, particularly the South Wales Institute of Engineers, Educational Trust, and Learned Society of Wales. Today, SWEET is represented by John Tucker here. Thank you, John. I'm also grateful for the in-kind support we have received from several external organizations. Although Zienkiewicz Lecture is an annual event, organizing this requires considerable behind-the-scene efforts. I am deeply indebted to Sam Board and Ruth Colton, I think they're somewhere, for their outstanding work in coordinating the lecture and ensuring its success year after year. Thank you, Sam and Ruth. With that, it is my pleasure to introduce the Vice Chancellor to come to the stage and introduce the speaker.
I only want to say a few words because, of course, I don't want to delay what we're really waiting for, which is to hear from Ian. But Diolch yn fawr, and thank you very much, Arasu. I too would just like to thank the committee that's behind all this work and the colleagues who've put so much hard work into bringing this lecture together. As we've heard, it's an annual event, so this is work that goes on all year round. And they do a fantastic job of finding really brilliant speakers, as we have today. So thanks a lot to all of you that do put in this work. As Arasu mentioned, the legacy of Oleg Zienkiewicz holds a huge resonance here in the university. I'm not an engineer, I'm a social scientist, so I can't pretend that I know all about his finite element method. But what I do know is that he was typical of what Swansea University is actually extremely well known for. And that is taking blue skies thinking, really imaginative, new, brilliant ideas, and then using those ideas and thinking about the impacts they're going to have. We probably don't have many better examples of somebody who's come up with a fantastic blue skies finding and then implementing it and thinking about where it's now used in industry. Our university was established over 100 years ago. Unlike many other universities, we were established by industry for industry. And that is in our DNA. Ever since then, we've collaborated with industry in much of what we do, but we also, of course, continue that blue skies brilliant research alongside it. And so many of those blue skies ideas are what stimulate the activity that we end up doing with industry. I could give all sorts of figures. I'll bore you with a couple. We're in the top 5 in the UK for spin-outs. Very few people in the UK realise that Swansea spins out more businesses than any other university except for Oxford and Cambridge. We are also in the top 5 for the number of grants we hold in collaboration with business, industry, public and private sector. It's in our spirit to work with partners and to bring those partners along with us and to learn from those partners and do everything we can in co-partnership. So it just seems so appropriate that we use this particular lecture to celebrate that culture that we have here in the university and something that we will continue to celebrate as we go forwards. More importantly about our speaker today, Sir Ian, of course, as you all are aware, is the Chief Executive of UKRI, the most important funding agency in the UK for research and innovation. It's a huge role and oversees a very significant budget which spans, of course, from engineering through all the work that many in this audience will be familiar with, but right through to the arts, humanities, social sciences, medicine and elsewhere. You'll know that means it's a hugely significant role, not just for the university sector, but for UK PLC. This is an organisation that helps drive innovation, economic growth and productivity, and it's really important that government, as they have done in recent times, continues to support that. Prior to leading UKRI, Ian was the CEO of the UK Atomic Energy Authority, which I suspect we might hear something about in a moment, and held a number of significant roles in fusion, particularly chairing the International AEA's International Fusion Research Committee. Obviously, he's a very renowned academic, published over 100 academic papers in this field, and his work has been recognised by a range of different bodies. A Fellow of the Institute for Physics in 2013, the Royal Society Kavli Medal in 2019, the Institute of Physics Glazebrook Medal for Leadership in 2021. I can keep going on, by the way, but elected Fellow of the Royal Academy of Engineering in 2022, and in 2023 got his knighthood in the New Year's Honours for the contribution that he's made to this discipline and all the work he's put into it. He's also, of course, a Fellow of the Royal Society. So we've got an extremely good speaker this evening. I'm really looking forward to hearing what you have to say, and I'm sure it'll be fascinating. And thank you very much for agreeing to come and being the next speaker in our Zienkiewicz Lecture. It's a privilege to have you here today. Sir Ian.
Good evening, folks. I can only disappoint you after that, can't I? So actually, on the theme of disappointing, I'm going to start by trying to depress you. So here's some data about climate change. This is data that was published by NASA about 3 years ago. It shows global temperatures averaged over the year, over the months of the year, right? So 140 years worth of climate data. And you see that not a lot happens for a long time. So this is going back, like I say, 140 years, and nothing's really changing. There's almost no excursions here from 0 degrees, which is the baseline at the start of the date, 1880 something. As you get to the 80s, things begin to change. So you begin to get a little bit of excursion from the 80s into the 90s, and then once you get into the 2000s, then things really, really begin to change. And you see more and more warming and warming. And we all see the effects that that has on our daily lives now. This, I think, this plot, the way that you now visualize this, I think really should alarm you. So the Industrial Revolution started more or less at the bottom of this curve, and nothing changes for 100 years, even though we're layering up carbon and carbon and more carbon and more carbon. That is the inertia in our climate, right? That's the inertia. And now it's going the wrong way, but the inertia has not disappeared. So turning a thing that's going the wrong way takes just as much effort as turning it did in the first place. This scares the living daylights out of me, this plot. It shows you just how hard it is to shift the system. So why? Where's all of our power come from? This shows you where power is generated around the world. If you go into North America to start with, it's a pretty big spread. Lots of different types of power sources. As you come into Europe, you see, okay, Scandinavia, really good at hydro. Switzerland, good at hydro. Southern Europe, not bad at solar. Again, bit of a mix. The continent of Africa, almost nothing. And that's going to change, but almost nothing there. And then as you go into Asia, and this is not a pejorative statement about India or about China, but a lot of coal, right? A lot of coal. And we can't dismiss that because we buy all of our product from those coal power stations, right? We've just sort of offshored carbon, but there is a lot of coal there, and that, by the way, is Three Gorges, that giant blue spike there. So this is the problem around the world, right? That our behaviour is not changing, and that is really baked in. That's really baked in. The assets there, if you just look at China as an example, if we were to get to net zero by 2050, for sure we've got to get rid of all the coal, right? For sure. We have to have no coal in 2050 and many other things besides. But that means that you would have to take off about 12 coal power stations a month. And at the moment, last year, we added net 4. So didn't take off 12, we added net 4. So this is a big, big problem. I think people are far too glib about the notion of getting to net zero by 2050. So I wanted to actually exemplify it. This is the way I talk to MPs about it. So really, really simple, even simpler than I use for my teenagers. So this is a build-up of where our energy comes from, right? Raw sources of energy in gigaton of oil equivalent. Don't really worry about the units. I've chosen that unit because it helps me make a point. Look at the black, the yellow, and the red, fossil fuels, okay? And okay, I'm 5 years out of date, but I haven't really changed a lot. In fact, it's gone up. So some two depressing things about this. Firstly, when I got into clean energy in 2000, we now burn nearly 50% more fossil fuels than we did then. Shocking, right? We knew about it. We knew it was a big issue, but yet we're continuing on a bad pathway. But I want to really exemplify the scale of the challenge because people are too glib about it and just assume it's going to work out fine. It's not going to work out fine, folks. So there's 11 gigaton of oil in the black, the yellow, and the red add up to, roughly speaking, 11 gigaton of oil equivalent. Okay? So that's 11,000 megatons of oil equivalent, right? Don't really worry about what a megaton of oil is. I'll come to that. Roughly speaking, 2050, we'll call it 11,000 days away. It's not, it's 9,500 days, but we'll call it 11,000 days to get rid of 11,000 megaton of oil, okay? And that is if we flatlined from here, but actually we're going north. But if we flatlined, that's what we'd have to do. So roughly speaking, you've got to get rid of a megaton of oil every day off energy generation. What's a megaton of oil? A megaton of oil is equivalent to the output of Sizewell, the largest nuclear power station in the country, or Hornsea, one of the biggest offshore wind farms in the world. You have to do that every day. Every day. We're lucky if we can build a nuclear power station a decade, let alone a day. But that's what we should be doing if we were actually to deal with this problem. Right? Again, if it doesn't scare you, it bloody well should. Because it's huge, right? This is absolutely mammoth. Right, I said I was going to depress you. I've hopefully achieved that. Let's talk about some solutions. So I say to politicians, you could do worse than take advice from Stephen Hawking. This is the last page of his last ever book, published posthumously, where he said, what do you want to see the world do? What would you like to see implemented by humanity? He says, this is easy. Sadly, fusion is not easy. I would like to see the development of fusion to give the unlimited supply of clean energy. So for those of you that don't know what that means, I'm going to do some basics, and then I'm going to talk mainly through some of the technical challenges that we face and how we go about overcoming them, and then hopefully an optimistic view of power plants at the end. So what is fusion? So fusion is taking the really light stuff, deuterium, tritium, two types of hydrogen. You force two types of hydrogen together. They don't want to come together. They naturally repel, so you have to give them a lot of energy to get them close enough to fuse, to bind together, and that produces helium and a neutron. And the neutron carries a lot of energy, which is actually one of the challenges. But that energy you can use to heat steam. Heat water turns it into steam, steam turns a turbine, produces electricity. Same old, same old. So it's just a fancy kettle, just a different way of all thermal plants work more or less in the same way. That process has loads of benefits. So it is inherently low carbon, so the only carbon is building the power plant in the first place. It will have a lot of concrete and steel in it, but then it doesn't produce any carbon in the actual generation process. It is inherently safe. So unlike conventional nuclear, where you get a risk of a runaway or a chain reaction that just can't happen. I spent 25 years of my life trying to keep it going. It's really easy to stop it, really easy. So it's inherently safe. It would be reliable in the sense that you don't have seasonal or weather variation. It's sustainable. Our fuel we just get from seawater and lithium. There are raw materials. I once did a calculation to work out if fusion worked, and I could replace all the known oil reserves in the world, all of the oil in the world with fusion instead, how much raw material would I need? And the answer is I would need 2 cubic kilometres of seawater. That's it, 2 cubic kilometres of seawater. The UK definitely has 2 cubic kilometres of seawater for all of the oil reserves in the world, right? So it's incredibly energy dense, incredibly efficient. To exemplify how efficient, for the rest of my life, even if I burnt electricity at 20 kilowatt hours a day, which I don't, even if I did, the rest of my life, the raw fuel I need is 1 bathtub of water and the lithium that you'd find in 2 laptop batteries. I own 2 laptops. I could go home and draw a bath. That's it. I'm good, right? So really, really low raw material. If bathtubs is not a good enough scientific unit for you, to compare that with coal, it's about 1,600 wheelbarrows of coal. So a lot of coal and then a lot of environmental damage and residue at the end. So all of that's good, right? All of that's good, but it is bloody hard. It's really hard to make fusion happen here on Earth. We know fusion works. It's the root source, actually, of all of our energy sources, because it is how the sun produces heat, which ultimately is how all the fossil fuels exist on this world, and solar and wind and everything comes from the sun. That happens in the sun because of the mass of the sun, right? So because it's so massive, you have this huge gravitational force which takes the hydrogen and helium and forces it together under immense gravitational pressure. We obviously cannot recreate the mass of the sun here on Earth, so instead we do it using making the fuel even hotter than the center of the sun. So we give it even more kinetic energy than you find in the center of the sun. So we have to take the fuel to about 150 million degrees, and only at 150 million degrees will it fuse. Now, when a fuel is 150 million degrees, it obviously can't touch the walls of whatever you've put it in, so you need to hold it away from the walls, and we do that in a device called a tokamak, using big magnets. So you see some big magnets that are wound around, and they sort of levitate the fuel away from the wall, keep it away from the wall, allowing us to take it to those temperatures. And that we can do. So we can get the fuel to that temperature. We can make fusion happen. Sustaining it is really hard, and I will talk through some of the other technical challenges. So I break it down to 5 things, 5 big technical challenges that we have to overcome to get to this, to get to a working fusion power plant. Actually, these lights come from fusion. The first one is the one that I think people probably know and I've just talked about, which is that we have to get the fuel to 10 times hotter than the center of the sun. That is a challenge, but it is something that we can do. But holding it at that temperature is really hard. This is footage from the inside of what was the world's largest fusion experiment. That fuel is 150 million degrees. So the image that you're seeing is 150 million degrees. And only at that temperature do you get a decent cross-section here between a deuteron, so this is heavy hydrogen, whizzing around the inside of the machine. And because you've given it so much energy, it will collide with a triton, very heavy hydrogen, two types of hydrogen. They produce a helium, just inert gas, right? So that's our product, just inert gas. And the neutrons. And the neutrons are very numerous and very energetic, about 7 times more energetic than a neutron in a fission process. So lots more energy that you can harvest. But the neutrons, being so energetic, actually damage whatever you build the machine from, the steel or the tungsten or the moly or whatever you might build the machine from. So this is meant to represent a steel, so it's in a lattice form, this is the atoms in the steel. As the neutrons pass through them, some will cause displacements on an atomic level of the atoms in the lattice, and that changes the properties of the steel. It changes how brittle it is, it changes how it creeps, its strength, which all affects the lifetime of the plant. And that ultimately affects the cost to the consumer, so whether it's commercially viable or not. The third challenge is how we extract the heat. So the bit in the middle I said is 150 million degrees. The wall has to be less than about 2,000 degrees or it melts. And then immediately behind the wall you have magnets which are cryogenically cooled to 4 Kelvin. So you've gone from 10 times hotter than the centre of the sun to almost absolute zero in 2.5 meters. It's quite a thermal gradient to deal with. The fourth challenge is where we get our fuel. I said we just get deuterium from seawater, but tritium, very heavy hydrogen, is radioactive, has a short half-life, about 12 years. There is no natural tritium left, all long since decayed. So we have to make it. This is meant to represent a blanket of lithium. So we wrap the machine in lithium. As the neutrons come out, they pass through that blanket of lithium and some will react and produce tritium. You then have to take the tritium out into a processing plant. You extract the tritium out of that solution. You freeze it into little pellets, and then you inject these pellets, so these little pellets of tritium that you keep injecting into the machine. And this is putting wood on the fire. If you stop putting wood on the fire, it stops burning, just like that. And then the last challenge is that it's a pretty unforgiving environment. Very high neutron load, in a vacuum, very, very hot. And so you can't send people in to fix things when they go wrong. And if you look at the inside, the armour is very shaped and specific, and things do melt, and they do go wrong. So you need to be able to get in and get out, but you can't send people in, which means you need robots to be able to fix things, and they're pretty big, complicated robots in a challenging environment. And then perhaps the most challenging thing of all is you've got to do all those 5 at once. And if we only had to do one of them, we'd probably solve fusion by now, but we have to do all 5 at once, and they often take you in orthogonal directions. So balancing those 5 different challenges all at once is actually the hardest bit. It's a proper systems engineering problem. Pleasingly, the UK is really good at this, by hook or by crook. And if somebody wants to ask me a political story of how we ended up in that position, save it for the questions, primed you. But we did, through European money largely. We ended up as the leaders in the world in fusion. And I can say that on an international stage and people don't laugh. And that's not true in many fields, right? But we are. You know, the US spend less money than we do on fusion, and they covet our fusion program. The Chinese are essentially trying to copy what we're doing and just building a replica of all of our facilities. We genuinely are the world leaders in fusion. And we do everything. So all of those 5 challenges that I just talked about, some countries are really good at 1 or 2 of those things, but nobody else can do all 5 of them. We're the only country in the world that does all 5 of them and actually thinks about the integration of the whole. And the big reason for that is that we hosted this facility. This facility is called JET. It's the largest fusion facility in the world. We hosted it for 40 years. It's a European machine, 87% funded by European money, the largest piece of European infrastructure on UK soil. So as you can imagine, Brexit was great fun for me. Here's a person, right, to give you a sense of scale. It's a proper industrial scale plant. There's nothing else like it in the world. The only machine of its scale, the only machine that's capable of running with tritium, with proper fusion fuels, the only machine with a robotic maintenance system, the only machine that would have the same armour that you'd use in a power plant, just unique. And my bad joke about JET is that it is both a literal and metaphorical big magnet. So everybody in fusion came to us, literally everybody in fusion came to us. I could be in Japan or in Korea or India and talk about this place called Culham, and they know where it was if they worked in the nuclear industry. They could point to it on a map, and Culham is a hamlet of 80 houses, right? So it is properly world famous, and everybody in our industry came through our place. Skip that. The second challenge I talked about was materials. Here's a good example of the damage that materials do. So I'm going to show you here a plot of pure tungsten. So it went in pure tungsten and got irradiated by neutrons. And you see that pretty quickly it's no longer pure tungsten. It's a whole bunch of other elements are coming into the mix of that alloy, and some pretty difficult things to deal with. You have a load of rhenium, tantalum, osmium, all of which really affect the material properties, fundamentally changing the strength of that material. That is a big problem. If your capital stack when you build the machine says the machine has to last 40 years or it's not commercial, the consumer won't buy it, and it only lasts 20 years, you have a big problem. Nobody will buy the electricity off you, and you have a stranded asset. So convincing investors to be able to put up the capital up front, be they public or private investors, when you don't know how long the machine's going to last, is a big challenge. So we've got to work out how long these materials are actually going to last. The way we do that is we put our samples into test reactors. We don't have a test reactor in the UK, so we use ones in Australia or in the US. They get irradiated by the neutrons. Then we bring them back to the UK. We take them through a series of materials analysis and testing equipment. I think we've got 24 different instruments now, which are all testing the materials properties. We then improve the recipes that we use for making the steel or making the tungsten alloys or making the components, as that's what's shown at the bottom here. We're improving the porosity of the steels here. And then we work with partners who pour steel, so to make a better steel that will last longer. And we are now pouring fusion-grade steels that work and can withstand the neutron loads at the multiple ton scale, working with steel manufacturers in the UK. So again, we are doing that whole loop and improving all the time. Skip that one. I talked about robotics. We opened a centre called RACE. This is one of those examples where you've worked out the acronym before you work out what it stands for. So it's Remote Applications in Challenging Environments. So Centre for Fusion Robotics. And this is the type of robots that we do. So up at the top, on the left-hand side, you can see we do all sorts of dissimilar robots. So lots of different robots are going to appear up there. Down at the bottom, our workhorse robot is a big boom robot. So it's a donut shape, our machine, and we need a robot to come in, be able to snake around that donut, pick things up, change things. So it needs to be able to wire, it needs to be able to weld, it needs to be able to cut, all at millimetre precision. That is all force feedback, so there's a user controlling the robot. It's all haptically controlled. That user is sat 500 feet from the actual robot, so it's all force feedback. But it can do things with really, really clever dexterity, high precision, to the extent that you could run the finger of the robot along the wall, and the user 500 feet away would feel this, would feel a millimetre step in their hands as they control the robot. So you can see we can do really highly dexterous things. There is basically no other robot like that in the world, to the extent that, after the Fukushima incident in Japan, you'd say the Japanese are good at robots, right? Hitachi, Mitsubishi, they've got people who build robots. After Fukushima, they sent lots of drones, ground-based robots, quadrupeds, all sorts of things into Fukushima to try to recover, first of all to analyse what was there and then to start recovering the fuel. And it's now a robot graveyard because they all got fried. All of those, the electronics on those robots got fried by the radiation. And eventually we said to them, what you need is a boom robot, because you put all the electronics at the back, and this is all mechanical. And eventually, the company that we spun out has now done the analysis robotics, a fishing line, basically 21-metre length boom robot that's gone into Fukushima, done the analysis, started to do sample retrieval. Hundreds of millions of contracts coming into UK industry on the basis of us developing those robots for fusion. Finally, I talked about tritium. So we are currently, my old organisation, are building a facility called HEAT, which is hydrogen-3 advanced technology. We went with hydrogen-3 rather than tritium because heat sounds better than TAT. What is in that facility is a very large, complicated processing plant. So we're moving tens of grams of fuel, but you have a 4-storey processing plant to move tens of grams of fuel. So there's very little fuel that's moved around the plant, but you need a big processing plant like this. The reason that we do that, and what we're doing here, is the full loop of tritium. So first of all, extracting it, we then freeze it to inject it into vacuum. You inject it into a container, it gets heated up, gets mixed with other gases, Then you have to extract those gases out the back end, separate the different impurities that might exist, take out the helium, and then separate the hydrogen isotopes. It's a complicated piece of chemical processing. But we're the best place to do that. The only place, by the way, that have been doing that for a fusion machine. So all of that sounds like there's some big research challenges to come. There are. But what about the future? How about actually putting power onto the grid? So the UK government have a plan for this. And I'm not usually very positive about the UK government, but it really does have a plan for how to get to prototype power plant. It has two objectives for that plant. Firstly, build a prototype. So they've committed to building a prototype power plant. I'll tell you about that in a minute. That actually produces net energy, and they're targeting doing that by 2040. So it's not forever and ever and ever away. It's actually 15 years, and we feel that pressure. 15 years to get it done. And the second thing is make some economic benefit out of this. God knows the UK has been in a leadership position in a bunch of industries and seen no economic benefit from it. So the really important bit is that we build a supply chain that is capable of exporting those things around the world. And folks say to me, what if the Chinese overtake you, or what if the US gets serious about fusion? They will, right? They will. Fusion is utterly disruptive in the energy market. They definitely will take market share. They will. They're the two biggest economies in the world. But if we get 10% market share, we have done a fabulous job. The UK is less than 1% of the energy market. If we captured 10% market share, that would be amazing, right? And the energy market is enormous. It's measured in trillions, right? So capturing that in the UK would be absolutely amazing. And that's what we're gunning for, not 100% of the market. It's not going to happen. What does a fusion power plant look like? What does it actually look like? The best way to show you that is to show you this machine. This facility called ITER. It's the largest scientific collaboration ever undertaken by humanity. In this partnership, you have Europe working with Russia. You have the United States working with China. And then for fun, you also have India, Japan, and South Korea. So that's basically most of the high profitable economies of the world all working together, all reliant on one another, which is a big social experiment as much as it is a big physics experiment. I'll show you a fly-through of this. So this is sited in the south of France. It's essentially, I showed you earlier, JET, the machine that we ran in the UK. It is JET twice as big, essentially. So it's twice the size in linear dimensions. And that, of course, when you turn that into volume, means it's 10 times, give or take, 10 times the volume. And at that point, this facility will produce 500 megawatts of fusion power. 500 megawatts is a significant amount of fusion power. That's sort of the consumption of Cardiff, probably, roughly about that, right? Just to give you some sense, so this site is a 40-hectare site in the south of France, which was always terrible to have to go there regularly. It has the biggest AC/DC distribution centre in Europe, has the largest cryogenic centre in the world. This is one of the magnets that goes around the outside. These are components of the vessel. So you see one upended here. These vessel components have to be sandwiched together. They are 60 meters in circumference. It's like a submarine sector. They have to be welded to 2.5 millimeter precision in a nuclear environment, so extremely high precision. This is just a phenomenal piece of engineering. Phenomenal piece of engineering. Incredibly difficult thing to do. But we're getting there. It's about 80% of the components are now on site. The project is actually going reasonably well in the last couple of years, despite some pretty big setbacks. The thing in yellow there is the first. There are now 7 stacked up on, this is a couple of years out of date, but there's 7 of these segments of a coil stacked up on one another. That magnet produces a magnetic impulse equivalent to the weight of an aircraft carrier. Just get your head around that. Put a magnet above an aircraft carrier, lift it out the ocean. That's how strong that magnet is. And in seriousness, when we started the procurement, when the project started the procurement of that magnet, the biggest magnet vendor in the world came back to the procurement team and said, have you got the decimal place in the wrong point? Right? So it was just a phenomenal thing. That project in itself is 10 times more superconducting strand than had ever been built in the world, ever, in the history of humanity, for one project. So it is building a whole supply chain, a whole industrial capability that didn't exist. As an example of that, I just mentioned superconducting strand. Here's a jacketing bench in California. This had to produce, not California, Florida. This is an 800-metre long jacketing bench. It's produced 4 miles of conduit in cable and conduit, which is the things that we wrap around the magnets, to extremely high precision. I said earlier that ITER is a project with all of these different international partners, all reliant on one another. That's true. If you were running a normal engineering project and you were building 18 magnets, the way you would do that is you would tender and find a supplier to build you 18 magnets on the same rig to the same spec. That's how you would do it if you were running an efficient engineering project. But this is a project where you've got the US working with China. Imagine I'm the US government and I've gone into this project and the Chinese won all the contracts to build the magnets. And now I want to build a power plant, but I can only buy the magnets from China because they're the only people with the factories and the competence of building the magnets. So they are reliant on everybody, on one another, but my 18 magnets are being built by 6 different partners. And imagine that that magnet is not the same spec as that magnet. Who compensates who and how much? So, you know, there's a lot of legalese and complexity in a contributions in kind project. And as an example of that, here's a jacketing bench in Florida. There's another one in China. So just building that bench is a hard thing to do, but you don't do it once, you do it 6 times. And then once you've made all the strand, you wind it onto a magnet, and then you have to impregnate that magnet with resin and bake it. And baking a magnet, which is 25 meters across, is a big job, hard thing to do. So how do you bake a magnet of that size? We have to put it in an oven. Well, no ovens exist, so we have to build an oven, which is a big civils project in its own right. That's a 48-meter wide oven, 20 meters deep, 5 meters tall, has to completely isothermically heat that thing, completely the same temperature everywhere. Big, complicated civils project. But you don't do it once, you do it multiple times, multiple ovens all around the world. So now you can see why the project actually, my bad joke on this is a bit like Wembley. Like Wembley, it's about twice over budget and about twice behind schedule. And it's about the same scale as Wembley, but it is more complicated than a football stadium. And this is one of the reasons that it's late, because you have this duplication of effort. Now, for this project, that's a really bad thing. For the future, it's a really good thing, because you now have some competition globally, where there are lots and lots of facilities like this all around the world, so you can drive a bit of competition in your supply chain. So that design is massive, right? It's absolutely huge. As you saw, everything about it is enormous. Things that look like submarine hulls having to be welded to precision, magnets that are bigger than any magnet that we've ever made. If a power plant looks like that, and that project alone will cost probably £30 billion, and if every time you build a power plant you have to raise 30 billion plus pounds, then you'll never get into the market, right? You know, we can build fission plants today, we know they work, but because they cost more than 30 billion, it's really hard to capitalise them. It's really hard to find the money for them. And that is actually what delays their penetration into the market, because other things are cheaper. So fusion can't be in that category, right? We can solve those 5 technical challenges, but if we don't make it at a cost that the consumer wants to buy, we'll never sell it. We'll never actually turn on the lights and it'll be fusion powered. My favourite quotation on this subject is from a chap called Walter Marshall, who used to run the Central Electricity Generating Board. All the power that we used in the 80s came from them. He knew a thing or two about providing power. This quotation, "There will come a time when we sustain a fusion reaction." Yeah, we've done that. Then we'll get as much energy out from the fusion reactor as we've put in. Well, actually, we can contend that we've done that too. However, there will never come a time when we get as much money out as we put in. And I used to drum this into my staff, that if we do not think how we do this commercially, if we do not think how can we do this at a ticket price that the consumer will pay, it is a complete waste of energy. I mean, both literal and personal energy. And it was always in my interests to make a difference to climate change. As I said, I scared you at the start, right? And so fusion has to actually address this issue. So how do we make it smaller? How do we make it cheaper? How do we make a thing that doesn't look like Wembley? Right? That is the crux of it. Now, fortunately, much, much cleverer people than me that came before me had already realised that the pathway through ITER and onto power plants looks gargantuan, looks expensive. So they said, well, hang on a minute, why don't we try to come up with an idea that makes the plant inherently much smaller? The reason that ITER is so expensive is that you have this magnetic cage the big magnet that I talked about lifting an aircraft carrier, that goes right down the middle. The fuel is out here in a donut. There's a big ring donut like this, an American donut type thing. The fuel out here, so you've paid for a magnet down the middle that produces 12.5 Teslas on the coil, right? 12.5 Teslas there. The fuel is out here, meters away, feels 5.5 Teslas. So you've paid for 12.5, you use 5.5. It's not super efficient. So people said, well, hang on a minute, why don't we just move the fuel much closer to the magnet? So it's still toroidally, topologically, it's still a torus, right? But it now looks spherical. So it looks much tighter, much closer to the magnet that sits down the middle. So it looks, our analogy is rather than a bike tire, it looks like a cord apple. So it looks spherical, but with a small hole down the middle. So, so we came up with this idea. We built the first one of these so-called spherical tokamaks, so it looks spherical. It was 7 times more efficient than the conventional way of doing it. So way, way more efficient, right? So you really can conceive of a much smaller plant which produces the same amount of power. And that's the important thing. Unlike in fission, where you build a bigger thing, it produces more power. More or less goes linear. You build a bigger thing, it produces more power. So a small modular reactor, if you've heard of those, Rolls-Royce designing small modular reactors, 440 megawatts. EDF building Hinkley or Sizewell will produce 3.5 gigawatts, right? So 7 times the power, but costs more. So it more or less goes linearly in fission. In fusion, you can produce the same power, but in a much smaller design. So that's the idea behind it. But, there's always a but, right? The but in this case is that I've told you that it has to be hotter than the center of the sun or it doesn't fuse. If I take something that's hotter than the center of the sun and I now put it into a smaller box, the chances of melting the walls of the box are obviously a lot higher. So most of the world, when we came up with this idea in the late 80s, early 90s, said, yeah, it's a nice idea. But if you scale that to a power plant, you're just going to melt the walls. And it's unsustainable. You have no way of extracting the heat. And we said, yeah, we agree, actually. With known technology, we have no way of extracting the heat, and it will just melt itself. So everybody else said, well, that's a dead end. It's never going to work. And we sort of raged against that machine and said, well, hang on a minute, yours is a dead end too, because it's so bloody expensive, nobody will buy it. So we said, well, we have to find a cheaper way. We have to find a smaller way of building power plants. And we came up with, this is how science should work. You have a problem that matters to people. If you can find an elegant solution to that, you can really make a difference to the world. So we came up with a solution to that. And I'll try to describe it. So the bit in the middle, the pink bit, is hot, right? Some of the material gets out to the edge. And in a conventional machine, these particles that sit in the middle, we use magnets to sweep them down to a sacrificial surface at the bottom. This is like the exhaust pipe on your car. So it's taking heat out, sweeping it down to the exhaust system at the bottom. In a small machine, that would still melt. So what we did was come up with this idea of saying, well, rather than hitting the wall there, which is how every other fusion device works, we're going to sweep our exhaust pipe around the corner. And in real estate, it's about 50 centimeters. It doesn't cost you a lot, doesn't take up a lot of room. But I just said that topologically, this is still a torus. So the particles are still going around and around and around. So in that 50 centimeters, they're going around and around and around. And 50 centimeters actually buys you 20 meters in pathway. So it's all the way up to the top of the stairs and back again. And as the particles move along that 20-meter pathway, they cool down. They radiate energy. They release energy. They spread their energy over a much bigger area. And so with this invention, we really think we can reduce the heat which gets to the wall. Now, it's a brave thing in science to publish what you expect to happen way before you can test it. So we did that. In 2010, we published this. This was our modeling prediction of what we thought would happen. Don't worry about the nomenclature. The red line is how every other fusion machine works. It's how ITER will work. So it's a lot of heat in a pretty short area. So the wetted area of the wall is not very big. It's a few centimeters, lots and lots of heat, very high heat density, right? So a lot of high heat density. The red line is how everybody else works. The blue line was what we thought we could do. And if you can reduce the heat, in this case, actually it's about a factor of 18. We always promised government 10 times, kept a bit in my back pocket. Said we'll aim for 10 times reduction. And in any field, if you have a product which is 10 times better than your competitor, I don't know, if I was selling you a mobile phone and I said my battery lasts 10 times as long as what you can buy off Apple, you would buy my product, right? You would buy my product. So if you can do 10 times better than your competitor, you have a major market advantage. So that's what we were aiming to do. I've got to say, when we published that, there was quite a lot of guffawing in the Fusion community. Never do this. We built a machine. It took us 7 years to build it. It was really hard. Lots of things went in the skip. Lots of things went wrong. And by the way, I think that's important in science. If you're not failing, you're not trying hard enough. So I really do think things should go in the skip. Anyway, we got there eventually. And within 3 months of turning it on, these were our first results. And if you want to see experiment match modeling, you could do worse, right? You could do worse. So this tells me two things. It tells me it works. We really, really can reduce the heat. In this case, about 25 times better than the conventional system. So massive improvement. And secondly, it tells me my models are not too far off what happens in real world. They're obviously not as precise, but not too far off. On the back of that, we said, look, we have IP. The UK is in a leadership position. We have a breadth of competence other people don't have. And we've got an invention that nobody else is pursuing that allows us to think about a much more compact power plant. We came up with a program called STEP. We're really bad for acronyms. Spherical tokamak for energy production. So the compact machine actually produces net energy. So that's the aim. But not just produce net energy, do it in a way that is much lower capital cost than the other approaches to fusion. Government have so far invested a bit over 300 million into the concept design of that. We passed through concept design last year. We're now into detailed engineering design. And in the latest budget process in the summer, government put another 1 billion into this to produce a detailed engineering design, get to what's called a development consent order, so approval to actually build this. And they're not just putting money into the design, right? So there's a whole lot of other things going on. Here's our high-level schedule. So we've done the first 4 years, 5 years actually. We have matured the concept. We've set up a regulatory framework. I'll say about that in a minute. We've chosen a site. I'll tell you about that in a minute. And we've set up a company. So all the things we said we'd do in the first 4 years, we have done. We're now into the detailed engineering design, by which point we'll start some long lead procurement. So magnets we'll start buying. We'll start the site development, so that doesn't end up being the critical path. The construction happens mainly over the 30s. It's about a 10-year construction period, aiming to complete construction by 2040. That is simultaneously incredibly aggressive and depressingly slow. It's both of those things at once. On a few of those things, so regulation, the UK is the first place in the world to regulate for how fusion will be regulated, so to legislate how fusion will be regulated. So we passed a law 2 years ago now, so it's on the books, to say that fusion will not be regulated in this country like fission. They both start with nuclear. They are completely different hazards, completely different hazards. And so why would you treat a thing using a fission regulation when it is a completely different radiological hazard? We won't. We're going to have a bespoke regime just for fusion. The first country to do that, now many others are following suit. So US followed after us. We expect Japan to do the same, Germany to do the same, a number of other countries to follow in our stead, but we went first. You need a site. You need to put it somewhere. So we ran a siting process. We had 15 nominations from all around the country, one from just down the corner, actually. We down-selected to 5, and we did detailed site analyses of those 5, and then chose this one. Up until, let me get it right, 2023, spring 2023, this was a coal power station operated by EDF. In fact, when it was built, it was the largest coal power station in Europe. On the Trent, down what's called Megawatt Valley, power station, all the way down the Trent, using British coal when it started. It's a massive site, 330 hectares, so absolutely enormous site. You can see the coal power station over to the right. There's a gas power station now built alongside to use the connection to the national grid, and you can see the coal yard, which is now all clear. And then what looks like virgin territory, lots of grass, is not grass. It's actually 6 million tons of pulverized flue ash, 6 million tons of it, which is why coal is a bad thing. So all of that needs restoring and dealing with. You can see we started over on the left-hand side to start digging out some of this ash. So there is a big civils job to do here, but there are lots of things to like about the site. It has a train line already. I don't have to run new train lines to bring in goods and people. It has a connection to the grid. I don't have to run new pylons and build a new substation. It has an abstraction license from the river. The Environment Agency gives a license to the site, not to the plant. So we already have a license for taking out water out the river and putting water back into the river. So, and there's population around there that is used to energy production and used to working in energy generation. So lots and lots of things to like. And then the last thing I was going to show you, just because it's fun, when I started in fusion a long time ago, I thought I'd be involved in lots of really cool technology and some really interesting research, and I'd make a difference. One thing I did not think I'd be doing was blowing up power stations. This is the coal power station. It is slowly coming down, and here's how they bring it down. So they actually just blow it up. And that's all gone now. All of that's gone. The thermal plant is gone. The cooling towers, which is the biggest thing on site, they come down in 2027, at which point the brownfield site will be pretty much clear and ready for us to start building from 2030 onwards. So we really are just getting on in our quiet British way with building a prototype power plant. The very last thing I was going to say was you need a company. So UKAEA is a government-owned organisation, a research organisation. It is not well suited to delivering a major infrastructure programme of this nature. But the fact is there is no fusion development company. They just don't exist anywhere in the world. So we decided to make one. So we've created a company called UK Industrial Fusion Solutions Limited, which is what you get when a minister names your company. And the first thing that company is doing is bringing on board partners. So it will always have UK as the fusion experts, as the people that really understand the technology, but it is contracting at the moment for a major engineering partner, which will almost certainly end up being a consortium of companies, and a construction partner, again, almost certainly going to be a consortium of companies. So they act at the top tier, sort of like the Terminal 5 approach for Heathrow. And then there's a big supply chain that we need to develop who do all of the different bits. And not all of that will be done in the UK, but we try to capture as much value in the UK as we can, a genuine public-private partnership. I'm going to finish with answering the inevitable question that somebody will definitely ask, which is when will we have fusion power plants? And I never answer the question. Instead, I quote Lev Artsimovich, who was one of the inventors of fusion, who was asked this at a press conference in the Soviet Union in the 70s. And I thought rather presciently, he said, fusion will be ready when society needs it. When we actually get serious about tackling the first 3 slides that I showed you today, which we are not, we are just not serious about tackling it at the moment. When we actually get serious about addressing climate change and we actually put money into clean energy, then fusion can be ready. I will leave you with another depressing thought, that last year in the world, we spent on extracting and exploring for fossil fuels, we spent over £500 billion. If we'd have spent that on clean energy, fusion would be ready, but we don't. And that, I will leave you there. Thank you.
My name is Howard Thomas. I'm here today as President of the Learned Society of Wales, and we're very, very pleased to be associated with the Zienkiewicz Lecture and especially with a lecture such as we've had today. I also have the distinction that I actually knew Oleg Zienkiewicz when I was a student here as an undergraduate when he was head of department. I don't know how many others are left, but I'm one of them anyway. Thank you, Ian, for an incredibly interesting.
Welcome.
I can see your enthusiasm coming out of every single pore. It's no wonder this project is going forward as well as it is. So without any further ado, let's take some questions. We haven't got an enormous amount of time, but let's start over there. And we've got a roving mic, have we? Yes. Good.
Thank you so much. That's a really inspiring talk, and I'm very much a convert towards this approach. I want to think more into the future now, decades into the future. Do you see fusion as being the pinnacle of energy generation, or part of a mix of energy generation methods, whether that's wind and solar? Do you think this displaces everything else, or do you think it's part of a network of activities?
Two things to say on that. It definitely is part of a portfolio. As with everything, balance is a good thing, right? You never want to be too exposed to any one thing in your diet. You don't just eat apples. With your money, you don't just put it into one thing, right? So you definitely want a portfolio approach, and it will depend on the natural resources of that place, right? I absolutely expect that in Northern Africa there will be a lot of solar, and in the UK we should do offshore wind, right? We're a small windy rock with a lot of sea. We should definitely do offshore wind. But that doesn't work for every country. There are some places that they just don't have any options other than to burn gas at the moment. And so that is where fusion plays into the market primarily. But you can't expect fusion to just come like that, right? We've got a crisis. We've got a thing that we need to deal with, and we need to deal with it today. Fusion will roll out, at the best. That first slide, I don't know if I can get back quickly, but the first slide I showed, this one. Look how long it took to take market share off coal, right? Gas is better than coal in every way. It's cheaper, it's easier to extract, you don't have to send people into the Earth's crust to dig it out, it's safer, it's better for the environment. Everything about it's better. But it took decades to take market share off coal. And that's primarily because building energy infrastructure is slow, right? It just is slow. And even if fusion rolled out at the growth rate of gas, which is pretty much the same growth rate as solar has been in the last 5 or 10 years, which is pretty much the same growth rate as nuclear was before the accidents curtailed the growth rate, they're kind of 25% yield year on year. You can assume fusion will be on the same basis. That means by the end of the century, we might be 10% market share, right? That's just the energy market. It's slow. It takes a long time. The second thing to say about the role of fusion is that I discussed one of the big challenges that we have is heat. We have too much bloody heat. But the things which are particularly hard to abate are things which need heat. So glass production, steel production, cement production, ammonia production. And that, that hard to abate sector is probably 20% of primary energy demand. And it's really hard to deal with because you need high-grade heat. And if you've got renewable energy, turning that into high-grade heat is super inefficient, super inefficient. Fusion just gives you high-grade heat. And so you could imagine a world where you build a fusion power plant and it produces precisely no electrons down a wire, so no electricity at all. In fact, you take electricity off the grid to run the plant, and instead it produces you 2 gigawatts of high-grade heat, which you use for industrial processes. Because that'd be much, much more efficient than building wind farms to produce hydrogen at low efficiency, and then burning hydrogen at low efficiency to produce the same high-grade heat. So I think there's lots of ways that it can enter the market, but all of that is driven by market dynamics.
Next question. Just at the back there. Thank you.
Thanks very much for that interesting talk, conveying the scale and magnitude of the challenges. So I have a more fundamental question. Is there a physical obstacle or a hurdle that you have to overcome to have sustained nuclear fusion? Are there plasma instabilities, or is it a case that you can't sustain these temperatures for long enough? What exactly is the challenge?
Yeah. I mean, there are lots of challenges. On the plasma specifically, so when you create this really hot gas, which becomes a plasma, it wobbles around. So you put so much energy, like I say, you're putting the energy equivalent to 10 times hotter than the center of the sun into a thing which is about 1,000 times thinner than air. So it has no structural integrity whatsoever, and you're pouring hundreds of megawatts of energy into it. And lo and behold, just like water down a pipe or air over an aeroplane wing, turns out to be quite a turbulent environment. And so it's not as stable as you want it to be. So we are constantly in force feedback, trying to keep this plasma as stationary as possible. And there are instabilities which happen in the middle of it and cause heat to move out to the edge and the fusion to be less efficient. There are instabilities which happen at the edge of it, which throw heat in quite an eruptive way out against the wall. And worst of all, there are instabilities which completely lose control of the fuel, and it just sort of throws itself up against the wall or down against the wall, which could, in extremis, damage the asset that you've just spent tens of billions building. And all three of those types of instabilities we have to control. We've got a handle on them, but I wouldn't say it's foolproof. As an example of that, at one point in JET's history, we decided to try and run the same experiment for 3 weeks. And we knew that when we ran it once, it worked fine. So we could start it, run it, end it. We tried to do the same thing for 3 weeks, didn't change a single thing, and 3% of the time, we lost control of it. And so that tells us that we don't have complete control over the start, the ramp, and the ramp down. And we need to have, because when you do that on a power plant scale, if 3% of the time you lose control over it, you do major damage, and then you have big outages, And when EDF have an outage, it hits their share price. So we can't afford to do that. So we have to get control of those types of things. And all the physics there is not completely understood yet.
And one more question. I'm really sorry because we've got people waiting for us for food upstairs, for those who keep calling for food. But there's one next for Win. And then, Arusu, I think we'll have to bring it to a close.
Thank you. Yes, a follow-on question is, how far are you with the current generation of spherical tokamak from maximum theoretical efficiency?
Oh, there's loads still to do. I mean, I would say that, as is true in every single power plant that's ever been built, the first generation is not the one that we have today. So there will be lots of improvements still to do. Sometimes government was saying, well, if we build a power plant, then why do we need UKAA? Well, why do we need to keep doing research in it? So because you constantly need to be improving your product and constantly refining your product. So I think there's loads that we can eke out in performance yet. Still loads to do.
And then just in front of you, did you want to ask a question? No. Okay. One last question for the semiconductor guys.
Not about semiconductors, though. Really about politics. The energy market is a failed market globally, and you have subsidies that are not factored into the cost of either gas or oil, particularly the cost of fighting wars and accessing those kind of things.
Yep.
And without trying to be sceptical, because it's a truly fascinating lecture, do you think you're using technological breakthroughs to try and solve what is actually a political cooperation problem?
Yeah. Yeah. I mean, you're right. The energy market is totally dysfunctional in many, many ways. But it does not belie the fact that if we had a way of producing primary energy that didn't burn fossil fuels, I still think that we could do that. But we don't have a commercial basis for doing that with any of the other approaches at the moment. They just don't scale, as you say. They don't scale because of the storage and the changes in the grids and all the other things that you need to do alongside renewables, and the fact that renewables are not equally distributed around the world and they're seasonal and all sorts of other things. And fusion is none of those things. It's primary energy in one place in a distributed grid in the way that we have it at the moment. So it should be, in principle, if you can get the strike price comparable to the existing sources, a much simpler way of transitioning.
So the drop in replacement, essentially.
Yeah. Which is why, one of the reasons why the notion of going from fossils to fusion on a coal power station is a really enticing prospect. To say, look, we're just replacing one for the other. Same site, same community, same connection to the grid, all the same infrastructure. Wouldn't that be a good way of rolling out? You don't need to completely change the way the grid works.
Look, thank you very much for taking the questions. And I'm sure there's lots more questions that people would like to ask. I do apologise, we're short of time. But it's my very pleasant duty now to actually present the Zienkiewicz medal to you.
Thank you so much.
So it's camera time, wherever the cameras are. Take a picture, if there is anyone.
Thank you.
Thank you so much. Thank you.
Thank you. Very kind of you.
Thank you.
Good evening. My name is Hans Zienkiewicz. I'm Deputy Vice Chancellor and Deputy Executive Dean of the Faculty of Science and Engineering. It's my job to close proceedings this afternoon or this evening, and I'm standing between the twins upstairs and you. So a big thank you, naturally, to Sir Ian for an absolutely fascinating lecture. I've learned a lot today, and maybe the future does look a lot brighter despite your first few slides when you started. Would like to thank, naturally, the sponsors and some sitting in the audience, so thank you very much. I would like to thank Paul for introducing the speaker, and I would like to thank Ruth and Sam for organizing, and Russell for being the chair and inspiring this lecture series. So thank you very much for everybody. And as said, there are drinks and upstairs in the gallery. We'll go there in a moment, but I would like to ask you to put your hands together once more for Sir Ian for the very good lecture. success.